Okay, today is lecture 29, if I'm reading correctly. So this is Nobel Prize week, right? So we'll try to do a couple of things that are related to Nobel Prizes, unfortunately only in economics, but physics is going to be a little bit too hard to get to. And there was an interesting article this weekend where even physicists are now saying they are trying to avoid things that have too much mathematics. And this leads to a very interesting discussion as to how much mathematics do you really need to have in your work. And for me, it's however much is necessary. The goal is to solve the problem. And if you can do that simply, that's wonderful. If you need more advanced mathematics, that's fine. Oftentimes, problems lead to the development of new mathematics. Have I told you all the story of the Battle of Midway? Have we done this? We've done that. So think of that in mind. What matters is solving the problem, not how much mathematics was needed. It was a really simple, elegant idea to figure out that AF-15 meant Midway. Okay, so what I want to do is I want to do Gale-Shapley. Is it L-E-Y? I think it's L-E-Y. How many of you have seen this before? Okay, one person, good. I don't mind boring Nathan, so this is fine. Oh, wait, was there someone else? Oh. Yeah. I'm sorry? Okay. So only 2 people have seen this. Okay, 3 people. Wow, it's going up 4. Okay. All right. How many of you have not seen Gale-Shapley? A lot of people have not seen it. So since some of you have seen it before, can someone describe what we're trying to solve? Yes.
We're trying to solve what's called the stable marriage problem.
Okay, so the stable marriage, and there's lots of different versions of this. So the simplest is we have n men, this is the classical formulation. We have n women, and we want to match each man with a unique woman and vice versa. If I just stop here, this is not a very difficult problem, right? How many ways are there to do this? And you've seen this before. I can't imagine what you like sorry. How many ways are there to match n men with n women, where each person is matched uniquely with someone on the other side? Yeah, n factorial. So number of ways equals n factorial, which by Stirling is approximately n to the n e to the minus n square root of 2 pi n. So there's a lot of possible matchings. Since this is a class in operations research, almost surely we're going to try to find a matching that is optimal in some sense. So we have to decide, what do we mean by optimal? So what we will assume is each man has a ranking of the women, and each woman have a ranking of the men. Okay? It will be based on good qualities such as, did they go to Williams? Were they a math stats major? Do they root for a Boston sports team? Things that really matter. Okay? Do they not worry so much about losing a goal line stand in a regular season versus a Super Bowl? Lots of things like this. What do you want to assume about the rankings of each person? I'm sorry? Uniqueness? So, it's not bad to assume uniqueness, but I don't think we need to assume uniqueness. You could have 2 people, maybe they're best friends, maybe they have a lot of similar qualities, and so they would rank people the same way. So it might be nice to have uniqueness, but uniqueness is not that important in the rankings.
Well, you need to establish whether one is good or bad.
I'm sorry?
You need to establish whether one is good or bad.
Yes, you want to have direction established. In the late 70s, my father was working in high tech, and we got to go to his company and play one of the earliest Star Trek games. And so we were in command of the Enterprise. A Klingon ship appeared. We had to allocate our energy between phasers, shields, and engines. We put 100% in phasers to just try to knock out the Klingons in one shot. We didn't realize the orientation of the axes, and we were off by 180 degrees. We had no shields. We were destroyed in one shot. And then this is DOS, so you basically see text scrolling up. The Enterprise has fallen. The burning Hulk is taken to Kronos. The Klingons march on Earth. The Federation fly. We're going like, Over a minus sign? Well, yeah, so it's important to establish which way you want things to go. This has been the last time I've been allowed to captain a ship for the Federation. So do you want to have one good or one bad? Good. First choice, second choice, third choice. So we'll have one as the highest. But what other kind of conditions do we want on our list?
Nothing more. You want everyone to have a ranking?
So we might want completeness. So there are some people who might say, you know, if I can't marry A, B, or C, or if I can't go to, Williams or Yale, I don't want to go to college. And then, fine, you're not going to go. So a lot of people in situations can actually have undue influence on their results by not ranking the entire space. So let's say you're trying to make sure everybody gets matched, and you want to try to maximize happiness somehow. And I bullet vote, and I say, I will only be happy if I get this, and I put down nothing else. So now when it's trying to evaluate me, what do you do? If you don't give me what I want, I'm completely unhappy. So you need to force everyone to rank all the alternatives. Hopefully somebody in this class will be doing a project for the elementary school. We've done this for the high school for Math Blast. We have this thing called Adventures in Learning, where it's like a 3 or 4 week January classes. It's a lot of fun. It's a nice linear programming problem. It's a scheduling problem. But some parents, hypothetically, have been gaming the system in previous years by bullet voting their children. I just want my kid to do this one activity. And then when you're trying to figure out the schedules, well, if we don't give so-and-so this one activity, they're going to be very upset, so we have to let them do this. And the people who are honest and list their backups are then penalized and don't have a chance to get into that. So you really want to think how you want to do this. This is extremely important. So we will assume completeness. All are ranked. Okay? There's one other thing that might be worth adding to our list. So when you're going through the ranks, what do you want to assume about the ranks that are assigned? I'm sorry? No ties. Why no ties? Yeah, because then what do we do if there's ties? This could give us maybe the possibility of cycling around. And if there's ties, that means you're essentially indifferent between the two. So would it be fine to then bump one of them up a little bit? A great thing to explore would be, well, let's say you actually were tied between two people. Could you end up having a significantly worse thing if you now bump one up over the other? Because before, you would have been fine with either, but now that you bumped this one up just a little bit, maybe it now has you go down a different branch of the algorithm. There could be some consequences by putting in no ties. What this is really saying is that if we look far enough, we can find a small fault in someone. We can find some way to split and distinguish between the two candidates. I don't like the way Miller writes his O's. That's not a really good circle. Professor Stoichu does a much better job. I'm going to take his class. Okay? If I lose to Stoichu based on how I write my O's, I'm quite happy with that. To be that competitive. But we will nitpick, we will find some way so that there's no longer a tie. It just makes the mathematics a lot easier. There's a lot of situations where you could use something like this. One of the classic ones is scheduling. You have a bunch of jobs and you're assigning people to a bunch of jobs. And each person has a preference, and you have a bunch of jobs that need to be filled. Anybody know an organization that does this? Doctors? In what sense?
Isn't that how they assign
residencies?
Yeah.
Yes. So you have basically people who have graduated, they've got the MDs, they're about to become a slave for a couple of years, and the question is, where should they be a slave? Which hospital? Which point of view do you adopt? Are you adopting, I want to maximize the happiness of the hospitals, of the doctors, or maybe some kind of mix? Do you think it's going to matter? Yes. You will get very different orderings depending on which perspective you take. And so one idea might be to maybe try to do a split the difference. They've actually changed the residency matching system over time. And they now actually try to take into account, do you have a significant other and would you like to be near them? Another situation where they use this is the army. You have a bunch of people who've just graduated and you have jobs that are going to be assigned. Sometimes they don't take a look at people's skills and they just assign people, here's the jobs, we'll put them in order, here's the recruits, and we'll just match them in order. It's a very simple algorithm. It can lead to some absurdities. One of my good friends from college and grad school, his father was a German major, and they needed somebody to work in a base in Germany. They didn't give it to him because that was the position that was being filled right before him, so they gave it to somebody who has no knowledge of German, and he got a job that he was really not well qualified for. But it was a very easy matching program. This is not that much harder to use. What kind of techniques do you think we know that would allow us to solve a problem like this? Linear programming. So the question is, can we solve by linear programming? And then there's another question, should we? All right, so the first question is, can we actually solve this using linear programming? What do you think? Yes, almost surely. Almost anything can be done with linear programming. It's wonderful. Here's a Rubik's Cube. Just in case people doubt it at home. All right, Rubik's Cube, right? Can I solve this using linear programming? So I only have finally many types of moves. You can have an initial state where it's mixed up. And then you have a string of moves. And then you want to see, you need an objective function. What do you want your objective function to be? Well, that would be to solve the Rubik's Cube quickly. I'm content to solve it. What's the goal? Yeah, minimize the difference from the solved. So if all pieces return to where they started, is it solved? So what you can do is you have a sequence of moves, and you see if at any point in the sequence of moves have you returned to the initial state. How would you do something like that if you have a string of, say, n moves? How would you check using linear programming, have I ever reached the solved state? So I have a sequence of moves. How would you check and see if it's solved after the first move? Just check and see if it's solved. How would you check and see if it's solved after the second move? Check and see if it's solved. Third move, check and see if it's solved. How would you check and see if it's solved after the first three, any time in the first three moves? What kind of command would you use? What kind of binary operation would we use if we want to just check and see if it's solved anywhere in the first three moves? Or. So you could do this with or statements. You know, if it's solved after one move, or it's solved after two moves, or it's solved after three moves, or it's solved after four moves. And what you could do is you could, if you want, try to minimize the number of moves that it takes to reach a solved state. Or you could say, let's try to see if we can solve the cube in one move. And you run the program. Doesn't work. Let's see if we can solve it in two moves. Run the program. Doesn't work. And you could keep doing something like this. For the 3 by 3, the God number is, I believe, 20. If you give the cube to the Almighty can solve it in at most 20 twists. Turns, whatever. No matter how the 3 by 3 is mixed up. 20 moves. No matter how it's mixed up. Basically, it's saying that any element in the group.
20 like algorithmic like changes.
No, 20 moves. 20 moves. 20 turns. That's basically saying that the order of any element in the group is at most 20. I don't know what the answer is for the 2 by 2. It's significantly less. All right? So you could actually set this up as a really good exercise. Set this up as a linear programming problem. I would never solve this with linear programming. But it's good to know what you can do. And it's good to get a sense of how long would it take. So just because we can do something one way does not mean that's the way we should do it. Could we set this up as a linear programming problem? Where we would have some kind of assignment. So for each person, we would have an assignment of the other side. We would make sure that it's mutually compatible. And then we would have some kind of objective function that would measure happiness. So depending on what the objective function is, we could solve this with linear programming. So let's try to think of what kind of conditions we want on our solution. So imagine we have an assignment now of men and women. I want the assignment to be stable. And so I'm not going to define stable, I'll let you define stable. What do you think it means for it to be stable?
So given any two matchings.
All right, so we'll have A and B and B.
So B wants B more than, so little b wants, wait, is that, big B's matched with little b?
Big B is matched with little b.
Okay. So little b wants big B more than little b wants big A, and big A wants little a more than big A wants little b is stable.
Okay, I think,
Or.
right. I think an easy way of saying it is it's stable if we're not in a situation where A prefers big B and big B prefers A, because then they could just switch and screw their partners. Right, which is what you say. This is, I think, a faster way to say it. Is it's stable if the following doesn't hold. Imagine big B and little a prefer each other to their mates. What they can say is, hey, if you ditch big A, I'll ditch little b, and we can run off together and do mathematics. And they go, deal. And then all of a sudden you now have A floating, you have B floating, and you have big B and little a together and happy. So it means that you can't have two people mutually improve themselves by dropping their current partners. Why do you think we want to assume a stable solution? Why do you think this is a desirable property?
I guess if we have a stable solution, we can't improve it, right?
You can't improve it.
According to the objective function that we talked about, right? If we have an unstable solution, then it's going to be a better one.
Well, not necessarily. It could be better just for these two, and it could be really screwing these people. Maybe, A and B hate each other. We could go back to ABBA. They used to be married. They don't want to get back together again. They despise each other. And maybe this is only a small gain. And so we could have a huge loss that's not going to be offset by a small gain. So overall, happiness could be decreased, but locally, happiness could increase. Bless you. Right now, am I concerned about local happiness? No. I have to think big. I have to think of all my students. I'm trying to maximize total happiness. If our solution was not stable, big B and little a have an incentive to leave their partners. Right? Is there anything that's stopping big B and little a from leaving their partners? No. They can make that decision, just the two of them, without having to get anyone else. If you have a longer thing of a cycle, hey, I'll leave my partner, and then you leave your partner, and then you leave your partner, and then we can move around the three of us. That's requiring multiple people to agree to the trade all at once, and you might be a little bit exposed. So for something like this, we want a stable solution, because if the solution is not stable, we would expect something like this to happen. Right? If the solution is not stable, well, then these two people can just leave, and then you would have this whole now, oh, B's available. Maybe I want little b now. Any James Bond fans? Any Bond fans? Anybody ever seen the movie Moonraker? One of my favorite lines is the bad guy is basically calling up Henchman R Us because his henchman is no longer available, and he needs a new muscle. And he hears that Jaws is available. Oh, well, if he's available, yes, I would love to have him. Please send him over. Okay? We're now in a situation where these two people are now floating. Do you think they're going to just match with each other? Or what do you think might happen? Yeah, when you start looking at all the other things, now you have C match with C, D match with D. Maybe, oh, I like B a little bit more than I like little c, and you could start propagating through the whole system. So the idea is that if the system is not stable, there is an incentive for people to, on their own, switch. Okay? So we will want things to be stable. The other things we want is optimal. each person is at least as happy as they would be in another matching, another stable matching. Let me just double check and make sure I'm phrasing this correctly. Yes? So we were trying to decide here, there could be multiple stable solutions. And we're trying to decide which of the stable solutions do we want. So the book has a nice example. The paper. This is a paper that was not published in one of the top math research journals. This was published in one of the general math journals. And it had incredible applications. Because we'll see that not only is there a solution in general that will be stable and optimal, but there's a fast way to find it. Significantly faster than order n factorial. It's going to be on order n squared. And n squared is essentially free. Okay? So here's an example. So we have, I'm sorry? Relative to n factorial, it's free. Relative to n factorial, it's free.
It's really strange to hear you say n squared is free. That's what we're always trying to run away from, you know?
It all depends on where you are. So we have 3 people, A, B, C, alpha, beta, gamma, and here are the preferences. 1, 3, 3, 1, 2, 2, 2, 2, 1, 3, 3, 1. Apologies for not memorizing this. 3, 1, 2, 2, 1, 3. So here are the men. Here are the women. Okay. And then the first number gives the ranking of the women by the men. So A's first choice is alpha, A's second choice is gamma, A's third choice is beta. So suggestions as to how we could find a stable matching. Or strategy. What would be one strategy? What's one possible strategy?
Pick randomly and hope for the best.
One is pick randomly and hope for this. For a lot of things, that actually works.
You could like go based on like what the guys prefer or girls.
Right, so which do you want to do, guys or girls? Girls. Okay, so basically we'll say, you know, the women get to choose. And one possibility is to say, let's look at each woman and give them their first choice. So for alpha, her first choice is C. So we'll do alpha with C. Beta's first choice is A. And gamma's first choice is B. And now you can begin to see that this is not a random set of numbers. What happens if we let women choose in this world?
They all pick someone different.
They all pick someone different, which is good, and that's not guaranteed. But at least it's good. We actually have a matching. Do the women have any incentive to change? No. They all got their top pick. What about the men? Do you notice anything about the men? Yeah, each man is assigned their least favorite alternative. But they got someone, right? What's another way we could have done this problem? From the men's first choice. So let's do it from the men's first choice. If we do it from the men's first choice, A would go with alpha. That might be why we have A and alpha. B would go with beta. And C would go with gamma. And in this case, what would happen? All the women would have their least favorite choice. Now notice that we are not giving a complete set of rankings. Right? I said that we want things to be complete. We are not listing everything. Well, if I wanted to, I could easily put the missing one right in the middle and keep this as last and keep that as first. And that wouldn't change anything. Wait, oh no, sorry, is it complete ranking? No. Oh, I'm sorry, no, sorry. I got confused. No, it's a complete ranking. I'm sorry. I was confused for a second. No, it's a complete ranking. So if we do it from the women's perspective, all the women are very happy and all the men are extremely unhappy. If we do it from the men's perspective, all the men are happy, all the women are extremely unhappy. Do the men have any incentive to switch? If B approaches any of these, well, B would never, because B is happy. If alpha or gamma approach B, B's not interested. Same from the other. So this example allows us to do a bunch of things. The first is that if a stable solution exists, it is not necessarily unique. So there can be multiple stable solutions. This is where operations research in some sense comes into play. If you only have one answer and you're trying to find the optimal among all feasibles, it's not really that hard when your search space is one element. When your search space contains multiple elements, that's where the mathematics can come into play. Where you now have to decide which of these should we choose. Okay? Do you think there are any other possibilities that would be stable? We could do all the twos. So we could do over here, so that would be B goes with alpha. Is that right? No, B's, yes. And then I probably should start with A though. A goes with gamma. B goes with alpha. And C goes with beta. Okay. Is this stable? So let's say alpha and gamma approach each other, and hopefully we can do things by symmetry. So right now we have B is with alpha, and let's say gamma comes over to B and says, I'd rather be with you. If B goes to gamma, is B happy? No. So B would not take an offer from gamma. What if beta approaches B? Would B be willing to switch to beta? Hell yeah, right? B wants beta. If beta approaches B, B is happy. Yeah, but beta won't have anything to do with B, right? How does beta view B? B is the least desirable. There's no way beta is going to go up to B in his dreams, right? I'm sorry? No, in his dreams, beta will come up to him. In her nightmare, she will come up to him. Okay? So there is no danger of beta coming up to B. If beta said to B, would you like to switch? B would switch with beta in a heartbeat. But there is no way beta is going to come up to B. So this shows you that there is no one who's going to switch with B where they're both going to be mutually happier. We should do the analysis technically for A and C. I think we can all assume that it's going to follow very similarly. That these numbers were chosen carefully. So what this shows you is this is a stable solution. This was stable and this was stable. Which one are you voting for? This is probably one where I might get different answers if people were voting publicly or if people were voting through secret ballot. Right? Depending on which group you're in, you have a chance of making your group do better. Or you could take the broader picture of which you think is better for society. Is it better for everybody to have their middle match versus the men or the women all get their best and the other ones get all their worst?
Is having your first choice like a linear to having your second choice? Like is that where free happiness?
Well, this is where you have to decide as to how much of a drop is it. One of the things sometimes you do is you could give 100 points. And you could say, how much is the first choice worth to you? How much is the second? How much is the third? But of course, if you do this, you can do a bullet vote and assign all 100 points. So what this is doing is, this is implicitly saying that it's almost like the same kind of drop among all of them. And that's not necessarily a reasonable thing. And this is where you have some opportunities to tweak the system. Yes?
Isn't there no optimal solution in
So each person is at least as happy as they would be in another stable matching. So here, it does seem like there would be no stable, it does seem like there would be no optimal here. In that, the men here are all extremely happy, the women are extremely unhappy, the women are extremely happy, the men are extremely unhappy. That, the definition I have of optimal is a stable assignment is called optimal if every applicant is at least as well off under it as any other stable assignment. Here's a stable assignment. Here's another stable assignment. A is clearly not as happy here as they are under this assignment. So I would say here there is no optimal solution. But there's a stable solution, yes.
Could you also maybe to make it like more of a to give an optimal solution, like if the women or the men have their like third choice, like that would like you would know that they were their last choice somehow, like that would come up eventually. Like when you become less happy.
We are leaving the realms of which I'm allowed to discuss. We will assume that it is done in such a way that they do not know that they are being settled. It's extremely unlikely that you're going to have people agreeing to matchings like this. And so, this is a little bit of a theoretical exercise when we're using phrases like marriage. But if you do things in terms of job assignments, in terms of residency, in terms of college admission, in previous years, certain colleges have been caught colluding on undergraduate admissions, both in terms of whom they accept and in terms of what kind of financial aid offers they make. So if somebody is deliberately giving a low financial aid offer, that makes another school more attractive. And there could be some agreements, we'll offer this much to these students, but not to these students. And so I know that Ivy Leagues and MIT were brought to court for stuff like that many, many years ago. So it is an interesting question as to whether or not people find out. This is why frequently when you hire people, you do not tell them if they were your first, second, third, or whatever choice. And a lot of information is kept secret. It can cause issues. I'm happy to say more about this when the camera is not rolling before class tomorrow or Wednesday. But this shows you the power of looking at just one simple example in terms of just how many things we can glean from this. There's not necessarily an optimal solution. There's not necessarily a unique stable solution. Could there be multiple optimal solutions? So,
really depends on your function.
right.
If you like
Wow.
to quadratic something, then maybe maybe look at the square versus ranking or something, right? Because if you like linear, then like
Well, so we're really not using an objective function. I'm saying if we wanted to do this with linear programming, we would have to introduce an objective function. What we're doing here is we're just looking at the rank.
I'm saying
Yeah.
it depends on what metric you use to describe like as happy.
Right.
If you're using a linear metric, right, where we say like their happiness is proportional to the ranking of their partner, like a linear ranking, then it's very likely possible.
Well, but the nice thing about the definition of optimal is it's not a sum of all happiness. It's for each person. It says each person is at least as happy. So it doesn't really matter what objective function you have. You can actually renormalize it so that it gives a rank of 1 to the first choice, 2 to the second choice, 3 to the third. Even though the actual happiness may not be linear, for the sake of analysis, we can assume a linear objective function. And this is nice when you can do simplifications like this. Because all we care about is relative ordering. How many of you have taken some classical mechanics class, intro physics at some point? Okay, what just happened? Gravity. All right, so what's happening? We're changing potential energy to kinetic energy. How do you calculate the potential energy? mgh. Okay, what's m? G. Gravity. H. What height? From where? From wherever I want. So I can do it from Alpha Centauri if I want? Yes, I can do it from Alpha Centauri. I really only care about the change in height. So you get to choose where ground zero is. For this problem, I would probably choose ground zero to be the floor. I really doubt that this is going to fall hard enough to go through the floor. right? Could do it from the ceiling. That would be another possibility. Ceiling is not great because it's different heights in different places. So I would probably measure it from the floor. Nope, didn't go lower. Whew. Right? So I can measure it from the floor. I really don't care about the actual value of potential energy. I only care about differences in potential energy. It's the same thing here. I don't care about the numerical value of someone's happiness. I just care about relative changes. So imagine we had two optimals. Imagine two optimals. So if we have two optimals, we can't have the same assignment everywhere. So there has to be at least one person who gets two different matches, right? And so in the first one, we could have maybe A is assigned with alpha in the first, and in the second, A is assigned with beta. Could they rank the two equally? No. In one of them, A has to have greater happiness than the other, because we assumed that there were no ties. No ties, so not equal. So we will not have two optimals. Okay, yes?
So you don't have to worry about putting a big B in there? Like, you don't have to worry about big B maybe now benefiting from this, so that, like, just even though this is less optimal for these people, it could be more optimal for some other person.
Well, it says optimal is each person is at least as happy as they would be in any other stable matching. Right. So that's the whole point. Is you always want to focus on as few things as possible. And so here, there is, of course, the people who are matched in the other cases. Where's beta originally matched? Where's alpha matched down here? We don't really need to know. If they're not identical, there has to be at least one man who has two different partners. Does there have to be at least one woman with two different partners? By symmetry, do we have to have something like that? Yes. So you could adopt either perspective. So someone has to be happier in one matching than the other. The total happiness might be significantly lower in one than another. And this may not be the best definition. Right? So when you're trying to figure out what do you want to do, what this is saying is, if you have one asshole, you're weighting them as much as everybody else. And you are so concerned about that one person being as happy as possible. Right? And we're just stuck with this person is in the system. Think of it almost as like the method of least squares when we're doing statistics and doing curve fitting, where if you have one bad data point that has a profound impact on the best fit curve. Over here, one person can have a huge impact on the solution. Do you think that this is the best way to measure how good a solution is? No. But why do we do this sometimes?
Feels mean to.
I'm sorry?
Feels mean to just screw somebody over.
It feels mean to screw someone over, and we feel like we're supposed to be kind people and take everyone's feelings into account. And even though little Garrick is quite annoying, we shouldn't just throw Garrick to the wolves. Right? Even Garrick deserves some happiness. And Garrick is really not a bad person once you get to know him. Why else might we do something like this? Yes? It's a lot easier. Right. It's easy to understand, and it sounds very easy to justify. And so a lot of times it comes down to not what is the best metric, but what is the metric that can be easily understood and agree, yes, that seems fair. And the hope is that it does a pretty good job in many situations. Okay, so we're happy with what it means to be optimal. We're happy with what it means to be stable. So we know that there can be at most one optimal. So here is a possible strategy. And then the first person to speak earlier today was from the women's side, so we will let the women be the deciding people and the men be the supplicants. Okay? The way it works is all the men will propose to the woman they desire most. And you know what she will say? She will only say one of two words. What are the two words? Nope. One of them is correct. One of the words she'll say is no. Maybe. Right? She's not going to commit so soon in the game. Let's see what kind of offers we have later. So men all propose to top available, to top choice. Women say say no or maybe. How many men do you think a woman would say maybe to at a given moment? One, the best. So only say maybe to best offer. So the men make their proposals. The women evaluate. No, hi, maybe. And then you have the bunch of rejects, all the men who, the person they said, will you marry me, they got a no. What do these men do now? Try again. What do they do now? Second choice. All right? So rejects, that's not a good word to use. The available men make offers to best alternative left. Actually, to make offers. Yeah.
Why don't we just amend the first statement to men all propose to top choice that they haven't yet proposed to, and then we'll just leave it at that 3-line.
Sure, top choice, good.
And then we're just done.
Haven't.
It's non-paired.
What?
Unpaired.
Yeah.
Unpaired,
True.
good.
And then we're done.
Unpaired men all propose to the top choice they haven't proposed to. Because if they've already proposed to this person, and they're not matched with that person, if they're not a maybe, that person has already rejected them because they've got somebody better. And the woman doesn't have to give up the person she has. So there's no way one of the reject men would ever get her. Right? So we can just do it as all the unpaired men propose to the top choice they haven't proposed to. The women say no or maybe. They only say maybe to the best offer. And then we repeat. Then lather, rinse, repeat. What are the hopes we have about this algorithm? It terminates in a finite amount of time. And that it will terminate in... Okay, so one is that it will terminate, another will terminate quickly. What else do we hope it will terminate in? That we'll find a stable matching. Right? That'll, Now again, which stable matching will it find? This is completely deterministic. Right? If only we had a set of men and women with rankings that we could run this on. Oh, good. All right, so let's see what happens. So over here, so round one. Okay? So A proposes to alpha, B proposes to beta, and C proposes to gamma. What happens? It's done. Algorithm terminates. I'm sorry? There are no more unpaired men.
Wouldn't they all be rejected?
No. So
The real part of the algorithm that's unwritten there is that if the woman is
Right.
Because there's no reason to say no.
Right. So I said only say maybe. I should really says maybe
The lemons we're going to prove are like
to best offer
like women's rankings
of
only go up,
new
right?
or reserve.
And that gives us our runtime.
So if like B and A had proposed alpha.
Right. So if B and A had both proposed to alpha, then alpha would have the ability to choose and shop. But unfortunately, the way this is set up, the men, by being the proposers, are actually able to maximize their happiness. The question becomes, is it better to be the group that proposes, or is it better to be the group that accepts the proposal? Or does it matter how these numbers are done? This is just one example. In this example, the algorithm terminates extremely rapidly. Right? Just one round. So what we'll do on the next class is we'll actually prove that this does run in polynomial time, that it runs in n squared time. And we'll talk a little bit about some of the consequences and some of the issues. It is possible to set this up as a linear programming problem, but it would be a binary integer programming problem. And binary integer programming problems are not pleasant to deal with. You know, we're not going to have a good runtime. Okay, good place to stop. Do we have a minute? No.